1, 2, 3. Проверка связи. 1, 2, 3. Так, ну что, не хочет? Так, значит, аппарат работает, да? Okay, well, let's continue. Well, let's remember what we did last week. We talked about homology with coefficients in an abelian group G, and we also defined cohomology with coefficients in G, and I stated the following theorem. We have the universal coefficient exact sequences. Okay, I will write the first one as the first one is the one that calculates the homology with the coefficients in G. Now, what do I have on the right? What do I have on the left? Does anyone remember? There is a tensor product of integral homology with G somewhere, and there is a Tour on the other side. So where do I have the Tour? Where do I have the homology tensor G? Tour on the right. Well, let's see. So this means Hn x tensor G on the left. Well, if we have an integral singular cycle, tensor it by G, we get a singular cycle. So this group maps into this one. We don't know yet that this map is injective or anything, but there's a natural map and it goes in this direction. In a while, hopefully in a short while, we will see that there is also a map in the opposite direction. But to begin with, there's this map, which means we have Tour And here there's a coefficient. There's an index. But what is it? Here I have n, here I have n, and here I have what? N minus 1. Okay. Well, there's a similar one. For cohomology. Now, does anyone remember the remaining two ingredients? We have hom on the left or on the right, and we have ext on the other side. So, which goes where? So, Wei says that here we have ext. Which means we have a hom on the right. Well, let's see. Let's remember that this co-chain complex, this cohomology is the cohomology of the co-chain complex, obtained by taking the singular chain complex and homming into G. Suppose I have a co-cycle. A co-cycle in the singular co-chain complex. I could take a cycle and evaluate the co-cycle on the cycle. Now, a co-cycle is zero on boundaries. It's not necessarily zero on all cycles, but it's zero on boundaries. So the result of evaluating a co-cycle on the cycle, in fact, depends only on the homology class of the cycle. So every co-cycle here gives me a map from Hn into G. Again, there's a map in the opposite direction, which is not canonical, and we'll talk about this later. So both sequences sequences are functorial, and they both split but they split non-functorially. Well, the first statement is clear, and the non-functoriality of the splitting is an exercise in one of the problem sheets, and we will actually we will see that this exercise is more or less completely obvious once we have seen cellular chains and co-chains. Okay, now where did we stop? We tried to define TOR and ext. And in the end, I talked a little, in the end of last week's class, I talked a little about projective resolutions and so on. What's your name? Tagir. Do you know what a projective resolution is? Yes, yes. So let's. A projective resolution of an R module M is where R is an associative ring with identity. A projective resolution of an R module M is a sequence of this is an exact sequence of this type, where all modules are projective, apart from M. Example. In the case which will more or less be the most important case for us, namely R equals Z, M equal a cyclic group of order M, small m. Then we have a projective resolution of the following kind: Z by M is the quotient of Z by the subgroup generated by M, which is precisely what it says here. Well, now I want to to state a theorem which is more or less straightforward, and I think it's well, the proof can be found in many places, and also it's relatively straightforward to prove the theorem just by diagram search and so on. The theorem is as follows. In this definition, it looks like we have M on the one hand, and the resolution on the other hand, and it would appear that M and the resolution have little to do with each other. Basically, it looks like we could take just more or less any projective resolution, and this resolution will not know anything about M. Well, this turns out not to be the case. How are modules related to projective resolutions? Suppose we have two modules, M and N. Again, we consider the case of an arbitrary associative ring with identity, which is well, because projective resolutions work more or less in the same way for all rings, more or less. So suppose we have two R modules. And suppose we have projective resolutions. And suppose we have a map of our modules. Which we call F. Then this map F extends to a map of the resolutions. In other words, we have a map Fi of our modules from Pi to Qi, and such that all the squares of the resulting big diagram commute. So let me put a P2, Q2, so, in other words, a map of modules induce a map of the resolutions, and moreover, which is also important, F is unique up to chain homotopy. Namely, well, we used to have colored chalks, and we don't have them anymore, which is a pity. Anyway, so suppose I have another collection of arrows, G0, G1, etc., which make the diagram commute. Then if I have another collection of arrows which make the diagram commute, then the chain maps F lower star and G lower star are chain homotopic. Is it clear to everyone what chain homotopic means? Tagir. Okay, so I will not try to draw the chain homotopies here because otherwise the diagram gets cluttered. This means there is a sequence of R module maps from Pn to Qn plus 1, such that if I apply delta n p, for example, I start here, end up here, and then I apply d n minus 1 plus dn composed with so for example, I start here, I apply the differential, then the homotopy. Apply the differential first, then the homotopy. Then I could do it the other way around. I could first apply the homotopy, then the differential. And the result should be Fn minus Gn. Okay. Now I will not prove this. I think. If you I suggest you try to prove this yourself, and if you try and you can't prove, please let me know. Well, why do we need this? We need to define derived functors. Suppose we have an additive right exact covariant functor. For example, tensoring by an R module when the ring is commutative is a right exact functor. Now, if the ring is not commutative, then we can also take the tensor product, but if we want this functor to take values in R modules again, we need R to be a bimodule. In other words, for non-commutative rings, this works as well, but there are some extra assumptions. Let's not worry too much about this case, because we will not need to deal with it in the sequel. Well. Okay, let me put an I at the bottom. And the definition of the ith the definition of the ith left-derived functor is as follows. We take a module, we take a projective resolution, we apply the functor. A resolution is exact. Any resolution is exact. But when we apply the functor, we get something which is no longer exact. And well, not necessarily. Could be, doesn't have to. And we calculate the ith homology module, and we get something, and we set this something to be the value of the ith derived functor, and this functor will be from R modules to R modules. Now, a functor is also supposed to do something with arrows, not just with objects. And we use the fact that this we use the fact that a map of modules induces a map of between any two projective resolutions. So basically, we choose a projective resolution for every module and use it to define the values of the functor, and then we we define the functor on morphisms using maps of the projective resolutions which make the diagram commute. Now the question is, why is the functor well defined on arrows? So this definition works. This definition works because whichever maps Fi we take, the map of the resolutions is well defined up to homotopy, which means after we apply after we apply F, we again get homotopic maps between F applied to the resolutions. And this means the induced homology maps are the same. So we get no ambiguity when we pass to the homology. And then basically it's straightforward to check that the identity morphism goes to the identity morphism, and also compositions go to composition. So we do get, in fact, a functor.
Am I right that for the same module we have some different projective resolutions?
Well, yes.
The result will be the same.
Yes, for example, we could take any resolution and add to it something which is projective and acyclic. This will be another resolution. Let's choose some resolution for every for each module. It doesn't matter which one. Let's choose one, and then we define the values of the functor on the objects and the values on the morphisms. And then a straightforward check shows that we do get, in fact, we do get a functor. Okay, now, there's there's a lot one could say about derived functors. This is just the very basics we need for our practical purposes. So I will not say anything else about derived functors, but basically there is a lot more to say, but we don't have the time. Anyway, I think I need to erase this beautiful diagram. So look at it again, and then it will be gone in 1 minute. Or less. Okay, now what else? So let's do an example. Let's take R equals Z, F F equal tensor G. Then we okay, well, instead of G, let me write B, because I would want to use another abelian group, A. The value of the ith derived functor on an abelian group A is denoted to AB, and we have the higher tours vanish, which is a consequence of the fact that R is a principal ideal domain, and there's only one tour, and since there is only one tour, people usually drop the index and just write tour. Well, let's see. Well, let's calculate tour let's calculate, so what are we trying to calculate? Let's calculate tour Zn Zm. So we take Zm. Sorry. No. Let me put an M here and then N here. Okay. Which doesn't really matter, as we will shortly see. So I take a projective resolution for Zm, tensor it by Zn. or more precisely, I should only take this part and tensor by Zn. What do I get? Well, I get Zn M Zn. Sorry, the arrow goes in, it doesn't really matter, but let's keep it consistent. So, I recall that a projective resolution starts in degree 0, and the grading or the differential is homological, meaning the differential decreases the degree. So we have degree 0, degree 1. Okay, now what happens when I calculate the degree 0 homology of this complex? What do I get? Well, I get some other finite cyclic group, but which one? For example, in degree 0, what do I get? Well, let's see. So Taguieff says it's the greatest common divisor. Okay. So this is the co-kernel of this map, and one can check that the kernel is exactly the same, up to isomorphism. Now, let me state a few general properties of left-derived functors and so on. Well, property 1, the zeroth derived functor is isomorphic to the functor we started with. And this works for every functor which is additive, right exact, and covariant. Another fact which is again which can be checked in a straightforward way. Tor is symmetric, meaning Tor AB is the same as Tor BA for any two abelian groups A and B. And this generalizes to R modules or for R an associative ring with identity. What else do we need? And property 3. Well, property 3, Tor A comma B is 0 if A or B, at least one of them, is flat. What does flat mean? Well, this means tensoring by this group is an exact functor. In general, this functor is only right exact, but sometimes it is exact, and if this is the case, we say that the group is flat. Which is this is more or less straightforward because suppose for example that B is flat. I take some projective resolution, a projective resolution for A. I tensor it by B, but tensoring by B is flat. The projective resolution was a cyclic, except in degree 0. So when I tensor it by B, I get something which is again a cyclic, except maybe in degree 0, which means all higher homology groups vanish. Well, this again generalizes to R modules, of course, But then we need to have, in order to use this the statement, we need to have a supply of flat modules. And a useful observation is that any torsion-free abelian group is flat. Not necessarily. Finitely generated or not. Let's see. A finitely generated torsion-free abelian group is just a finite sum of z's. Z is flat as a module over itself. Why? Well, basically because tensoring by Z is the identity functor, and hence it is exact. Well, tensoring by Z plus Z is just the sum of two copies of the identity functor, and so on. So for finitely generated, this is not very surprising. Well, every abelian group is the direct limit of its finitely generated subgroups. Suppose I have an arbitrary abelian group. Suppose I have an arbitrary abelian group, then the group is the direct limit of finitely generated abelian subgroups. This functor is the direct limit of tensoring by the finitely generated subgroups. which is something one needs to check.
And probably one thing to say here is that this is filtered limit, so
Yes, and a direct limit of exact functors is again exact. Okay. Now, what else do we need to know? Basically, we using this, we can calculate all so corollary suppose suppose I have two groups A and B which are on this list. Then to AB tour AB is 0, except when both groups are finite cyclic, and in this case the tour is Z by the GCD, as we have seen a few minutes ago. Let me briefly state the properties of the Ext functor. And the proofs are exactly the same or very similar, so I will not say I will basically not say anything about this. But first of all, we need to define the Ext functor. Now, suppose we have a left exact contravariant functor. Example, left exact, contravariant, and additive. for, there are lots of functors which aren't additive. I'm not saying anything about this. Functor, a functor from where to where? Let's say from R modules to R modules, where R is an associative commutative ring with identity. As an example, let's take F let's take hom into some fixed module M. Well, this functor is contravariant, more or less clear. It's additive, again, more or less clear. Left exact, well, what does left exact mean? Well, it's the same, well, it's basically the same as right exact, except we replace right by left. But there is a slightly tricky tricky issue. The functor is contravariant, and contravariant functors mess up the right and the left. So let's figure out what this how this works in examples. Well, let me take my favorite short exact sequence. Okay, now let me take M equal 2. I don't really need anything else. Now let me take here M by 2 as M, and what do I get? Well, I get 0, Z by 2, and then I get what? I get, again, Z by 2. And 0. Except this map will be multiplication by 2, which means it will be 0. Well, the sequence is not exact. The exactness fails here. this map is 0, so it cannot be surjective. On the other hand, if I take this part, I transform it into this part. If I forget the 0, the sequence which I get here will be exact. So left exact in this case means means the following thing. The functor takes exact sequences of this form to exact sequences of this form. So we get a genuine intuitive left exact functor if we replace the source category with its opposite category. Otherwise, well, the rest is completely straightforward. Now we define the derived functors in exactly the same way as in the previous case. But this time we call them the right derived functors. Namely, we take an R module M. We apply, we take any projective resolution, we apply the functor, and we get a co-chain complex instead of a chain complex. Why? Well, because the functor is contravariant. Well, I get a co-chain complex. I calculate the cohomology modules or groups of this complex, and I set those to be the values of the functor Ri of f at the object M, and this is the ith right derived functor of f. let me calculate one example. So example, let's again take R equals Z, F equal hom into Z by M. Well, what do I have? Let me take A equal, let me take an N here and an M here. Oh, by the way, I forgot to say that if F is common to M, then the ith derived functor is denoted ext I comma M. Okay, well, let me just calculate one example, and then we'll have a break. So R equals Z, M equal Z by M. Well, what do? I take the projective resolution of Z by M. Well, let me take this one. Okay, then I apply hom into Z by M. And we get the same, basically the same complex as the one we got when we calculated Tor.
Shouldn't the R be from 0 to 1?
Oh yeah, thank you. Exactly. But the cohomology will be the same. Namely, we get Z by the GCD, both in degree 0 and 1. So we calculated so X Z by N Z by M is Z by GCD Mn. which is the same answer we got when we calculated Tour. Well, we will see in a minute that Ext is not the same as Tour. But before that, we need a break. Are there any questions? Well,
The example of X to maps is taken from the same from that diagram.
yes. Yes, we take one resolution and another resolution. And basically, when we apply F, the functor F, we get a map of the F of the resolutions, and this map is unique up to homotopy. F is additive, which means that it takes homotopic maps to homotopic maps. It does not always take quasi-isomorphisms to quasi-isomorphisms, but it does take homotopic maps to homotopic maps. By the way, I keep saying additive, additive, but does this word make any sense? So wait, what does this word mean? Well, F, just like any functor, gives a map of the sets of morphisms. But R modules is an abelian category, in particular, it's an additive category, which means the sets of maps are in fact abelian groups, and a functor is additive if the induced map of the sets of maps is in fact a map of abelian groups. And again, there is a much fancier way to state all this, but let's not do it. Let's have a break instead. is the recording running? Good. Okay, well, where were we? Yes, we have defined the x functor, and we've calculated the value of this functor in one example. Well, let's calculate another example. Let's calculate x from z by m to z, which is very similar. We take the same projective resolution, and but this time, instead of homing into z by n, we hom into z. So we get what do we get? Well, we get basically we get the same thing, except there we'll go in the opposite direction. And the result is z by m in degree 1. So the x in this case were x1 there aren't any higher x for the same reason as let me put it here. So if R is Z, then all higher x vanish. And we have only one x, which is why we drop the 1 and write simply x. Okay, so we get z by m, but if we swap the variables, we get 0. Basically, z is already projective. So we just take the projective resolution, which only has one z in degree 0 and zeros elsewhere, and we get this answer. And the conclusion as opposed to tour, X is not symmetric. So again, I will list a few properties of X. Well, the first property, let me put it in a more general way. The zeroth derived functor is the functor itself. Contravariant, yes. The higher x's vanish if the first variable is projective or the second is injective. We already know what projective is for general modules. This means a direct summand of a free module. Now, what is injective? Injective is a bit more complicated, but for abelian groups, there is an explicit description. A module is injective if and only if it's a direct sum of z's, of q's and q by z's. And this direct sum may well be infinite, uncountable, and so on. And similarly, there is a simpler description for projective modules. For our equals z, and namely for r equals z, projective and free are the same. Well, we know how to calculate x AB for AB cyclic. What happens if we want to include Q? If we put Q at the second place, we get 0. Why? Well, because Q is injective. But X from Q to Z is quite complicated, and in fact this group is isomorphic to R. More precisely, to the additive group of R. And there is also X from Q to Z by N, and I don't remember what the answer is. And it's either 0 or something which resembles R. No idea. Well, I have an idea of where one could find the answer, but I don't remember what the answer is. Okay, so we have seen a few basic facts about X, and we know how to calculate it in some examples, but as this example shows, the result is sometimes complicated, especially when the first group is infinitely generated, something like Q. Okay. Are there any questions? Well, let's prove the universal coefficient theorem. The proofs, there are two exact sequences, and the proofs are very similar. So let's do one of those. Well, at least now we understand what all the ingredients are. We know what Tor is, and we know the rest. Okay, well, let's construct this short exact sequence. The proof works for any free for any chain complex of free abelian groups. For example, we could take the singular chain complex of a space X, or the simplicial chain complex of a delta set, and so on. we have this short exact sequence of chain complexes where on the left we have the graded group of cycles viewed as a chain complex with zero differential. And on the right, likewise, we have the graded group of boundaries viewed as a chain complex, again with zero differential. Does this make sense, Tagir? Okay. Everything is free in this chain complex. Well, C. C is free. Every component of C lower star is free by assumption. But then Z and B also have this property. Why? Well, because every submodule of a free module is free when the ring is Z. Yes, but this quotient also lives in C degree of degree star minus 1. So they're all free. So all components of all complexes are free. So, in each degree, the sequence is not just exact, it is split exact. Tagir, does the phrase split exact have any meaning?
Am I right? That means just that the in the middle is the direct sum.
Well, yes, and more precisely, there is a complementary subgroup here which maps isomorphically to this one. So when we take the sequence and tensor it by G, this sequence, tensor it by G, we get again an exact sequence of complexes. Well, let's see. Okay. Let's write the resulting long exact sequence of the homology groups. Well, let's see if we recognize all the characters. Well, this one is familiar. This is the group we're after. It's the nth homology group of this complex tensored by G. So this one, this character is also familiar, and so is this one. What are these arrows? Well, these arrows are the Bockstein homomorphisms. The Bockstein homomorphisms go from the nth cohomology of this complex to n minus first cohomology of this complex. Well, the nth cohomology of this one is this group, and the n minus first is this group. Now, my claim is, and we also know that B is a subset of Z. And my claim is the Bockstein is exactly the inclusion of B into Z tensored by G. this is diagram chase. Let's chase some diagrams. So we have Zn goes to Cn, and okay, I'll tensor everything by G. Okay, 0, something, 0. Well, I look at this diagram. What do I see? Well, there's, suppose I have an element of this complex. Well, an element of this complex is
Actually, tensor G somehow seems doesn't do anything here.
say again?
I mean, tensor G doesn't do anything here, so probably we can just leave it to the last.
It doesn't really do anything, but we want to see what happens when we do tensor. So let's keep it. Let me take an element here. I want to lift it first here, and then apply the differential, and then take basically the element of this group, which goes to the image of the differential. So we take this, we lift, and we get the sum of deltas Ci tensor Gi. We get Ci tensor Gi such that delta Ci is Bi. Is this, yes, this is allowed because every element of V is the image of, is delta of something. Okay? And then we applied delta. Delta transforms every Ci again into Bi. But this time we consider it as an element of Cn-1 tensor G. So we see that the Box-Stein homomorphism in this case is just the identical inclusion. Why? This is an element of. Let me put it like this. So this is an element of this group, which we consider as a subgroup of this group. And this, by definition, is the Bockstein of this element. Okay, so well, let me call this this map IN, and then this one will become IN minus 1. From this long exact sequence, we get the following thing. We get the following short exact sequence. We just take the co-kernel of this map. It's a subgroup of Hn. C level star tensor G, and this subjects onto the kernel of this map, IN minus 1. Tagir, do you agree?
I always forgot what I'm always forgetting most of the kernels.
Okay, but what is kernel?
Kernel is the pre-image of 0.
The pre-image of 0. And the co-kernel is the quotient by the image. Wait, kernel and co-kernel. Okay, now Bn goes to Zn. The inclusion of Bn into Zn is in effect a projective resolution of Hn. Well, yes. So this is well, this is a short exact sequence, and what's important is that both Bn and Zn are projective. Why? Well, because they are free. And here we use the fact that we work with Z modules. If we had a more complicated ring instead of Z, then basically, instead of a short exact sequence, we would get a spectral sequence. Okay, now what happens when we take this and tensor by Z? Well, tensor by G. We get we take this part and tensor by G. We get a complex, and this complex may have homology in degree 0 and in degree 1. Now, the co-kernel of this map is simply 2 or 0 of Hn comma G, but 2 or 0 is simply the tensor product. So the first term here is just the tensor product of the nth homology of C and G. Well, this is how we defined the derived functors. We take a resolution, apply the functor to it. Well, in our case, the functor is tensoring by G. We take this resolution, tensor by G. We get a complex. The homology of this complex in degree 0, on the one hand, is precisely the co-kernel of the map. On the other hand, the homology in degree 0 is the 0th derived functor. And the 0th derived functor is simply the functor itself. Okay, so we know the co-kernel. But now, for the same reason, the kernel is 201 Hn minus 1 comma G. Which is simply just the tour, because there aren't any higher tours in our case. Okay, now we have the long exact sequence we're after. Well, we take the same complex, but we replace n with n minus 1. And then we apply the functor tensoring by G. The kernel of the result, by definition, will be the first derived functor. And the first derived functor is 201. Or just 2. Okay, now we want to know why the sequence splits. We have constructed the sequence we're after, and it's clear from the construction that the sequence is natural, but we want to know whether or not it splits. Well, to construct the splitting, we want to construct a dotted arrow such that the composition is the identity of Hn tensor G. Well, let's try to do this. Well, to do this, we observe that there is a chain map from C to H. That extends the map, well, the natural map from Z to H. Well, the chain map means here we have the given differential, and here the differential is 0. And why? Why is this true? Well, because Cn is isomorphic to Zn plus Bn minus 1 prime. Where Zn is just a group of cycles, and Bn minus 1 prime many happy returns. Bn prime, Bn minus 1 prime, what is it? It's something which maps isomorphically to Bn minus 1. So we take any splitting like this, and we define the chain map to be 0 on n minus 1 prime. Why is the result a chain map? Well, let's see. The differential takes the differential is 0 on Zn, and it's also 0 on the cohomology. So the chain condition on this summand is clear. As for the other summand, the differential takes b n minus 1 isomorphically to b n minus 1, b n minus 1 prime isomorphically to b n minus 1, and then to 0, because in cohomology b n minus 1 becomes 0. On the one hand, and on the other hand, if we compose in the other order, we take bn minus 1 prime to 0 straight away. So we do get a chain map. Well, let's tensor everything by G. What do we get? We get a chain map from C lower star tensor G to H lower star tensor G that extends the natural map from Z tensor G to H tensor G. And then we apply homology. We get a map of the homology groups. And this map of the homology groups has the property that if we have a cycle and in C, and tensor it by G. Some small g. That takes a cycle tensor G to the class of the cycle tensor G. And from the construction of this arrow, it follows that this map has the property we're after. Yes, we apply the homology functor to this chain map, where here we have the given differential tensor the identity of G, and here we simply have the zero differential.
And because of zero differential, the second part is the same.
Yes, the second part is the target is the same, and but here, when we take homology, we get this. And we did use several times the fact that every subgroup of a free abelian group is again free. And over more general rings, there is, well, instead of a short exact sequence, there is something more complicated. But on the other hand, over a field, things become simpler. We don't have any tours and exts. Over a field, we simply forget this this part. On the other hand, over more general rings, there's this part, and the rest of it. Okay, now my claim, we have proved the homological case of the universal coefficient theorem. My claim is the cohomological case is exactly the same or very similar, and we will not talk about it in any more detail. And I think it's I think we're supposed to. Yes, we're probably supposed to stop at this point. Okay. Are there any questions? Well, let's call it a day. And well, next week there will be a class, same as this week. I don't think there are any more holidays. And at some point, probably we will have another extra meeting on Saturday, but let's do this in the end of the semester, so we know exactly what we want to do.